Hello everybody. Okay, now what I'm going to do is try to explain how these amplifier V in, V out graphs actually work. So we'll go through a couple of examples. Now in this first example you can see that we've got a V in, V out graph, and in all cases, in every V in, V out graph, the vertical axis is always the output voltage and the horizontal axis is always the input voltage. Notice that in this example, the output voltage is in volts and the input voltage is in the units of millivolts. Okay, so the first example will have a sine wave going in, and I'll draw a little mini graph of it. So there's our input voltage going in. This is our input voltage, or V in. And let's say its peak value is 150 millivolts. And its minimum value is negative 150 millivolts. What we want to do is look at what the output voltage would look like. So we're going to be able to draw a graph of the output voltage. Now this is obviously not drawn to scale, and the units on the vertical axis will be different. Here, this is the input voltage in millivolts, and this will be the output voltage in volts. So the best way to do this is to look at the peak-to-peak voltage. The peak-to-peak voltage is that distance there. So V peak to peak is actually equal to 300 millivolts. Okay, so if we know the peak-to-peak of the input voltage, we should be able to work out the peak-to-peak of the output voltage if we know by what factor it's being amplified, or the gain. Now remember, the gain of an amplifier is simply equal to the gradient of the linear region of the graph. And the linear region is this region in here, this zone in here, and this zone here are not part of the linear region. So let's work out the gradient of this graph. So we'll take that coordinate and that coordinate, and we can see by looking at this graph and using the rise over the run that the gradient of this graph is in fact 16 over, that's 16 volts divided by 400 millivolts. Well, we need to have consistent units, so we're going to write that as 16 over 0.4 volts. So that actually equals 40. So the gain of this amplifier is 40. Now remember, the gain has no units. So, because we now know the gain is 40, we know that our input voltage is simply going to be amplified by a factor of 40. Now we also notice that the linear region of the graph has a positive gradient. It's sloping upwards, which means that this amplifier will not be inverting. It is a non-inverting amplifier. Which means that the shape of the output graph will be the same orientation as the shape of the input graph. And in fact, the only difference is the amplitude. It'll be 40 times larger. So, 40 times, if a peak-to-peak is 300, if the peak-to-peak is 300, and we shall multiply that by 40 to work out what the peak-to-peak of the output is, then that's going to equal 12,000. 12,000 millivolts. So in other words, the peak-to-peak of the input, which was from 150 to negative 150, a total of 300 millivolts, we multiply that by the gain of the amplifier, which gives us an output voltage of 12,000 millivolts, which actually equals 12 volts. So we now know that the output voltage will have the same period, so it'll cut the time axis at the same points. Please excuse my terrible drawing. The only difference is now these voltages will be much larger, and because the new peak-to-peak is 12 volts, from there to there is 12, therefore the peak must be 6. So there'll be 6 volts there and negative 6 volts there. And that's pretty much all there is to this particular example. Now I'll put some new values in here. Let's say that this is 12, and this is negative 12, and this is 500, and this is negative 500. Once again, our horizontal axis is in millivolts, and our vertical axis is in volts. Now, it won't always necessarily be in millivolts along here, but whatever the units are, they will be specified on the graph. So you need to make sure you identify the units of your graph, okay? So that you know what you're dealing with. Okay, let's make this a little bit trickier. Let's say, in this example, that our input voltage looks like this. Sine wave going in. This is our V input volt, V in. Now this time the input voltage is peaking out at 700 and minimizing at negative 700 millivolts. This is our time axis along here, measured in milliseconds. Okay, so let's see if we can work out the output of this graph. Well, once again, we can identify the peak-to-peak. In this case, the peak-to-peak is 1400 millivolts. So V peak-to-peak equals 1400 millivolts. Now, we wish to know what the output voltage is going to be like, and after we take the signal and amplify it through this amplifier. Now, because I've substituted new values here, we have to recalculate the gain. And in this case, the gain of our amplifier will be the change in V out divided by the change in V in, and the safest way to do this is just look at the total change in V out, which is from 12 to negative 12. So that's a change of 24 volts over a change of from 500 to negative 500, that's 1000 millivolts. So it's 24 volts over 1000 millivolts, which is the same as 24 volts divided by 1 volt, which is a gain of 24. Okay, so that tells us that the input peak-to-peak is going to be amplified by a factor of 24. Simple enough. Now, there is one complicating factor, and that is if we look at our input range, and I'll highlight that in a different colour. If we look at an input range, it goes from negative 500 to 500. And you'll notice that if the input goes below negative 500, or if it goes above 500, there is no further change in the output. In other words, even though the input is increasing, the output still remains at 12 volts. So any input voltage that goes beyond negative 500, in other words, extends out this way, any input voltage that extends beyond negative 500 or goes beyond positive 500 will be clipped. Okay? It will be clipped. So that means that if we now draw our output graph, here's our V out graph with time, and we once again note that the graph, because it's positive, it's a positive gain, so it does not invert, so the output will be non-inverted. The output voltage, peak to peak, will be 33,600 millivolts. So I'll just draw that lightly. So I'll draw a light graph. It's a very shocking diagram. And if everything was going perfectly, then that peak to peak would be 33,600, which means that the peak would be 16.8 volts. So we'd expect that value there to be 16.8. And this would be negative 16.8. Now how did I get those numbers? I actually converted 33,600 millivolts to volts, which is 33.6. So the peak to peak is 33.6. Therefore, half of that value from there to there will be half of 33.6, which is 16.8. Now, there's one thing we haven't taken into consideration, that is the fact that it clipped. Now we know that when the input voltage gets to 700, when it gets to 500, I beg your pardon, the voltage is clipped. So that means that this top portion, there and there and there and there, when it comes to the output side, will be clipped. So let's work out the corresponding values. Well, we don't actually have to work them out because they're on our graph. We can see that when the input is at 500, which is the clipping point, the output is at negative 12. And when the input is at 500, the output is 12, which means that the maximum voltage that can be achieved by this amplifier is 12 volts, and the minimum value is negative 12. So the actual clipping point is going to be at 12 and negative 12. So if we were now to draw the correct graph, it will look like this. So this part's fine, this amplified fine, but now it's clipped, amplified, clipped, and of course this would be a symmetrical graph, and so on. So that's actually what the signal would look like. So these top regions here and these regions here are clipped away. And of course that leads to distortion. Okay, in this final problem I've tried to make it really, really difficult, just to see how you would go. This would be about as challenging as it could possibly get on a Year 12 physics exam regarding amplifiers. Now let's just go through what we've got here. We've got an amplifier V in, V out graph. Here's our V out scale and here's our V in. V out is in volts, V in is in millivolts. You'll notice that the graph is skewed to one side. It's not symmetrical anymore. So that's the one key thing we need that's made it difficult for this graph. Secondly, here's our input voltage. So this is a graph of our V in millivolts. You'll notice that it's not centering on 0. This blue axis is the key axis, so that's 0 there. So you can see that this particular input graph is centering around the 100 millivolt mark, and it goes as high as 250 and goes as low as negative 150. So the AC signal has been offset. Now, what we want to do, if we want to see what happens if we put this AC signal into this amplifier, what will the output look like? Now, that's about as challenging as they get, as I said. Okay, so let's have a closer look. The first thing I've done here is work out the gain of our amplifier. And we do that by actually calculating the change in the output voltage divided by the change in the input voltage. And the output voltage change in this linear region, it goes from 4 to negative 10, which is a total of 14 volts. At the same time, the input is changing between 200 and negative 80. So that's a total of 280 millivolts. So our gain becomes 14 volts over 280 millivolts, which is 14,000 millivolts over 280 millivolts, which is a gain of 50. Now, because the gradient is a negative gradient, it's sloping downwards, that means that our gradient will be negative and that it is classed as an inverting amplifier. And what that means to us is that when we go to graph the output voltage, what the graph of the output voltage looks like, it'll be tipped upside down. So it'll be an upside down version of this graph. Now, the other thing I've gone ahead and done is worked out the peak-to-peak voltage of our input. Because we knew it is peaking out at 250 and it is going as low as negative 50, that's a total range of 300 millivolts. So our peak-to-peak voltage of our input is 300 millivolts. Okay, so now I've added a few extra things to the input graph. I've marked in the clipping points. So we know, we're looking at our V in V out graph, we know that if the graph goes beyond 200 millivolts, that no more change in output is possible. So that's one of our clipping points. The other clipping point occurs if the input drops below negative 80 millivolts. If it drops any further than that, there is no further change in the output, it just remains constant. So that's the other clipping point. And so what I've done, I've indicated those two clipping values on our input graph. So we know it's going to clip if our input goes above 200 or below negative 80. And as we can see, because I've superimposed these lines on our graph, we can see that the negative side of our graph is not going to clip. It doesn't cross the negative 80 line. So this lower part of the graph is safe. It is the upper part of the graph that crosses the 200 red line. So that's telling us that that section in here and this section in here are going to clip. So we're going to lose that part of the signal. Okay, so that's giving us a nice visual clue of what to expect. So one side of the graph will be clipped, but the other side will not. Now the next thing is I've indicated the center line of our input. Now we know that our center line of our input signal is 100 millivolts. It's not 0, it's 100. So what we want to do then is find out what is the corresponding center line for our output voltage. And you can see here that I've drawn it in at negative 5. Well, let's find out how we got that. How do we know that our output voltage is going to center on negative 5? Well, it's quite simple really, because all we know that if we feed in 100 millivolts into our graph, so here's our input side, 100 millivolts, we go down to the line here, and we read off the output, we can see that because this is halfway between 0 and 200, that would be 100, this is going to be halfway between 0 and 10, which will be negative 5. So when the input is at 100 millivolts, I beg your pardon, the output will be at negative 5. So every time the input is there, or here, or here, or any of those points, it will actually be on the negative 5 volt line on the output. Okay, so that's giving us a bit of an idea now of where the graph is going to be situated on our output graph. So we've now identified the center line of our output. So now, remembering that this line here, this blue line here is our 0 line, that's 0. Here's -5, that's going to be the center line of our output. Now, you'll notice there's another mark here I've just placed, which is 2.5 millivolt line. Well, let's have a look at why that's there. We'll get to that right now. So, let's look at the clipping side first. We know that as the graph goes higher than 100, if it goes higher than 100 and crosses the 200 line, it's going to clip. So as it goes from 100 to 200 and goes beyond, that part will be clipped. So, but remember it's inverting. So remember, it's starting here. Remember, if it's at 100 here on the input, it's at -5 on the output. And as the graph is going up on the input, it's going to be going down on the output because it's an inverting amplifier. So it'll go down to a maximum value of -10 volts. The amplifier cannot produce an output greater than -10. So it'll bottom out at -10 volts. And remain bottomed out, and it will remain bottomed out until it starts to return again. So as it returns, we'll get that sort of effect. So this section here is flat. Not very obvious on my graph, but it is. That's flat. Now on the other side, as the graph drops below 100, we remember that it doesn't cross the clipping line. So that full part of the signal is going to be amplified without clipping. So we want to know, well, what's that voltage there? What's that change in voltage there to work out what the output is? Well, it's gone from 100, this V peak value, V peak, is from 100 to -50. So the peak value, which is half of the peak to peak, is going to be 150 millivolts. And we know that 150 millivolts is going to be amplified without being clipped. What's our amplifying factor? It's 50. So we know that it's going to be multiplied by a factor of 50. So our gain factor is 50. So 150 multiplied by 50 is in fact 7,500. And that actually equals 7.5 volts. And because we now know that the output peak is 7.5 volts, then we know it's going to rise 7.5 volts above the center line. So it'll go from here, it will move up, have a peak value of 7.5 volts. Now from -5, 7.5 will take us to positive 2.5 volts. So the graph will look like this. So this side was clipped. It didn't get any further than -10, even though it should have perhaps continued if it wasn't going to be clipped. This side here has not been clipped, and so we just took that peak voltage of 150 volts, multiplied it by the gain to work out that the peak output is 7.5 volts. But because the center line of our graph was at -5, we have to add 7.5 to that, which brings us to positive 2.5 as the maximum value. So there is the output of that graph. And remember that in any amplifier, the period of the output or the frequency of the output will not be any different to that of the input. So the time scale will be the same for both the input and the output graphs. All that will change is the amplification factor and whether part of the signal is clipped or not. The only other thing that can change is the output graph flipped upside down or not. So there we have a couple of examples which hopefully will help you work your way through those amplifier problems. Thank you.